All right, well, welcome back to Lean Together 2025. Our next talk is by Jean-Baptiste Tristan on verified foundations for differential privacy. Take it away.
Thank you. Hi, everyone. My goal today is to introduce you to SAMCERT, which is a library of verified differential privacy primitives that is implemented in Lean. And more specifically, I'd like to discuss the implementation and verification of one specific primitive in SAMCERT, which has made its way into a cloud service. It's called AWS Clean Rooms Differential Privacy. So what I'd like to explain is first how we implement in Lean a randomized algorithm. Then I'd like to explain why MATLAB was really critical to the verification of the properties of the algorithm. And finally, I'll say a few words about how we deploy and how we have two choices, either metaprogramming or FFI to deploy into the service. To get started, I'd like to introduce you to a distribution, which is the main character in this story. It's called the discrete Gaussian distribution. It has two parameters, a location and a scale. It's defined on the integers. And if a random variable is distributed according to the discrete Gaussian distribution, then it has the PMF that you can see in this slide, where the numerator is a Gaussian function, and as I think you would expect, but the normalizer is defined differently, but it's a normalizer for this Gaussian function defined on the integers. If you want to know more about this distribution, which has lots of interesting properties, I highly recommend a paper called The Discrete Gaussian for Differential Privacy by Cannon, Kamath, and Steinke. Now, why do we care about this distribution? It has lots of good properties, but there are two that are going to be relevant to us in this talk. The first one is that it has a property that's relevant to the field of differential privacy, because the discrete Gaussian satisfies a specific version of differential privacy called concentrated differential privacy. And I'd like to try to explain, to give an intuition or explain a little bit what this property is. So if we have two reals, epsilon and delta, greater than 0, and let's say that we have a query. So here the query is Q. And this query is a function that if you run it on some database where you have a bunch of record of type X, so here the database is X bar N, it's going to compute something and return an integer. That may be a statistic, for example. But we're going to assume that it has a peculiar property, which is that if we have two databases, X and X prime, which have the property that X prime differs from X by only a single record, meaning that maybe X prime has one more record than X or one less, or maybe that they have the same number of records, the same records except for one of them. We're going to assume that the absolute value between running the query on X minus running the query on X prime is bounded by delta. Well, if that's a property holds for Q, then if I sample from the discrete Gaussian by using the scale delta squared divided by epsilon squared, then we have the property on the fourth line, which is that for any alpha, the Renyi divergence of order alpha between the distribution Q applied to X plus Y and the distribution Q applied to X prime plus Y is bounded by 1/2 epsilon squared alpha. And if you're not familiar with Renyi divergence of order alpha, it's fine, it doesn't matter, just it's a divergence. And so intuitively, it allows us to compare distributions and ensure that they're not too different. Again, if you're interested in knowing more about this topic, I highly recommend a paper called Concentrated Differential Privacy, Simplification, Extensions, and Lower Bounds by Markman and Thomas Steinke. All right, so I don't want to give a talk about differential privacy. So I'll just, in one slide, try to explain why this property is useful in practice. And that's basically just rereading again this statement. So let's say that you have some data and you want to run some query on it. Maybe you want to compute a histogram, but you want to preserve the privacy of individuals in a data set. The idea of differential privacy is that we're going to add noise to that query, but in a principled way to provide some mathematical guarantee. And intuitively, at a high level, what this guarantee is going to do is that if we were to have another database where we have only one a record, either like we add a record or we remove one or we modify a record, and then we were to run the query again with the noise, then we'd obtain a different histogram, but also we have different distributions of our histogram. And the property of concentrated differential privacy is going to ensure that these distributions are not going to be too different, right? And so the intuition is that it's meant to, we add noise to make it difficult or to provide guarantees that we won't be able to extract information about a single individual or a single record. So that's the big picture. The other property that is very important because we need to run this. This needs to run efficiently. Is that we can sample from this distribution. There are known algorithms to sample from the discrete Gaussian distribution, and they have a set of good properties. First, they can be implemented from just fair IID coin flips. If the location and the scale are rational, then there are algorithms that are going to be closed. All of the operations will be closed on the field of rational numbers. Also very important, they, in the worst case, use constant space, despite the rational being of arbitrary precision. And the runtime is constant in expectation. In fact, there are much better bound than this, but I don't want to dive too much into this. So the goal, now that I've introduced these two things about the discrete Gaussian distribution, is we want to implement a sampler in Lean for the distribution, and we want to prove that it satisfies the concentrate DP property. I should say a word about why do we care about doing verification for this. There are, at a high level, three main reasons. One is that it's a safety critical primitive. Bias in the sampler can result in privacy loss. And there are actually papers that show how biases can be used to recover information from single individuals from a database. And it's particularly important to get the sampler right because it's at the core of the entire privacy infrastructure. Everything that builds, everything that has to be differentially private is going to build on this sampling algorithm. Of course, we do a lot of testing, but testing is statistical. So for example, we test the first 4 moments. That's essentially mean, variance, skew, and kurtosis. But we also do non-parametric tests like Kolmogorov-Smirnov. But this is far from perfect. It's expensive. And finally, there's another reason, which is that once we have a proof, it enables optimizations that can sometimes be quite tricky. And here, I don't want to look closely at this piece of code, but this is an example. If you want to sample from a geometric distribution with the parameter that you can see here, there's the usual simple algorithm that we know of, but there is also something that for some values of S and T might be much more efficient, and that's what you see on the right. So that's one example of the kind of optimizations that you may want to be able to do, and then verifying that you have not modified the distribution is important. Okay, so I want to start explaining how we do this? First of all, and it's a bit of a caricature, but note that there are two things that are at least conceptually easy to do in Lean. One is to verify functional properties of randomized algorithms. For example, you might implement quicksort, it's randomized, but if what you want to prove is that quicksort is indeed correctly sorting, the randomness isn't actually of fundamental importance in that reasoning. Vice versa, you sometimes have deterministic algorithms that have probabilistic properties. One example of this would be, for example, some versions of linear regressions. So here you can just implement them as normal functions in Lean, and then when you reason about them, you just use probability theory. In this case, we're going to deal with both randomization and probability. That's something I find particularly interesting because that makes the verification more challenging and more interesting. In SAMSERT, to do this, we introduce a type, slang, and this type in Lean is going to be defined as a type of function from alpha to extended non-negative reals. Now, the key about this is that depending on whether we are in Lean doing some reasoning or whether we're executing the code, we're going to interpret this type differently. So within Lean, when we do the implementation and when we reason about the code, this type is going to represent unnormalized distributions. However, when we're going to execute our code, it's going to take on a different interpretation as randomized computations. So slang, you'll see, I think of it sometimes as a type for representing randomized computation or sometimes distributions. So to be a little more concrete, let me explain how slang is defined. Basically, there are just a few primitives in Lean. The first one is prob uniform byte, which is just a discrete uniform distribution of size 256. We have a function prob pure that's essentially an indicator function. We have another function prob bind that takes both a randomized computation p and then a function f that if you give it some value of type t is going to be another randomized computation. And we compose them by integrating f with respect to p, the randomized computation. And finally, we're going to have a function prob 0 that just associates mass 0 to all of the possible outcomes. What's more interesting are loops. Note that these algorithms, like the one that the sampler for the discrete Gaussian, it's full of loops that terminate with probability 1. So we can't use structural recursion to implement these algorithms. So the way we approach this is first we define a function prob wildcut, which is essentially if you have a condition, a body, and some state that is being passed by this loop, is going to unfold the loop n times. So it's defined simply as we look at n. If n is 0, then we run out of iterations to do. We return the mass function 0. If it's n plus 1, then we're going to do potentially one unfolding. So first we look at the condition applied to the state. If it's true, we apply the body to the state, we get a new value, and we call the function recursively to do the rest of the unfolding. Otherwise, we just return the state. So for different values of n, we have different functions, and we're going to define the actual while loop for condition, a body, and some initial value as the supremum of the sequence of functions for the different number of unfolding. Okay, so that was for the Lean side, where we interpret slang as distributions. Once we execute, then we need to have some operational semantics for all of these constructions. And prop pure of A is going to correspond to just returning the value A. Prop bind of a randomized computation P followed by F is going to correspond to sampling from P. You get X, and then you apply X to function F. The prob uniform byte corresponds to reading one byte from your random, for example. And the prob while is going to correspond to a loop where you start by initializing a state, and then you have a while loop that keeps updating the state by applying the body until the condition is false. The implementation of the sampler is not too surprising. So in Lean, we're going to use these S-lang primitives. We're going to write computations of type S-lang. Essentially, that amounts to writing a rejection sampling, or I'm using the term loosely, so it's like an accept reject. And then we implement sampler for uniform, Bernoulli, geometric, von Neumann, discrete Laplace, and discrete Gaussian. And here I just show you one example of the kind of sampler. So if at some point we need to, for a value gamma between 0 and 1, we need to sample from Bernoulli of exponential minus gamma. And one algorithm to do this is you take a counter, initialize that 1, and then you're going to repeat sampling from a Bernoulli parameterized by gamma divided by k, the counter. And if A is 0, you exit the loop. Otherwise, if A is 1, you're going to increment the counter and continue. Once you're done with this, if k is odd, you return 1. Otherwise, if k is even, you return 0. Okay, so once we have our implementation, we need to deploy this. So we need to get the executable code. And as I said, we have two options. One thing we have done, they're both implemented in the library. One thing we have done is to extract to another language called Daphne, which has multiple transpiler. So we extract first to Daphne, and then from Daphne, we can transpile to Python or Java, etc. And so then we have, for example, Python code that we can deploy. The alternative is to use the Lean FFI to define in C++ the meaning of all of these S-lang primitives. One thing I should add is that so far I've talked mostly about unnormalized distributions, but once we do the deployment, if you want to execute, regardless of whether it's through extraction or with the FFI, you need to make sure that what you're dealing with are proper distributions. And so we have to prove, of course, that eventually all of these S-lang computation are normalized. Okay, so that was implementation and deployment. What about the proof? So the proof essentially has two big steps. The first thing is that we need to characterize the distribution or the PMF for all of these distributions. So coming back to the example I showed earlier, we are going to have to do reasoning that is roughly described by the last two lines, right? We're going to reason about once this piece of code has been executed, I have some value of k star. What is the probability that k star is greater than k? It's the probability then that a1, a2, etc. are all equal to 1, which ends up being gamma power k divided by k factorial. And then what is the probability that k star is going to be odd? It's the infinite series of the probability of k star being equal to odd numbers. And then if you do a little bit of rewriting, you end up with a formula that's going to allow you to get to exponential minus gamma. So here, that's one example where we see the use, how useful MATLAB is, because, for example, we need to show that this sampler eventually that give rise to a distribution that mention the exponential distribution or the exponential function, sorry. And so we make use of like the analysis in MATLAB to show these kind of results. Another thing that's worth mentioning is how do we really do this reasoning about the loops? Because the difficulty, the big part of the difficulty isn't actually the mathematics of it that I was showing before, but more how do we characterize the PMF given that our loop is defined as the supremum of this sequence of function. One reason why it's not, at least to me, not completely trivial is that often the way we reason about functions defined in this way is using Scott induction principles, but they're not very useful to characterize PMFs. So what we do instead in SemSert is that we directly show pointwise convergence without trying to use some Scott-like induction principle. Even then, even if you consider a specific outcome, it's not completely trivial because the mass sequence of one outcome can be quite unwieldy. Another thing to note about this proof is that it involves a lot of going back and forth between the reals and the extended non-negative reals, because sometimes we need a group structure, sometimes we need the lattice structure, and that's really an annoying part of the proof. So to explain how we deal with it, we characterize these PMFs. Note that if we look at geometric 1/2, essentially what happens when we define it is that it starts with all zeros. And then when we fold once, it's 0.5 followed by zeros. If we unfold twice, 0.5, 0.25 followed by zeros, etc. For something like rejection sampling or accept rejects, it's very different, the pattern, because each outcome evolves according to some mass function. So for example, if we consider the PMF 0.1, 0.7, and 0.2, and then we reject until the outcome is 0 or 2, then the first function is zeros everywhere, then it's 0.10, 0.2, then it's 0.17, 0.34, etc. The reason I'm saying this is that in the end, all of these loops that I mentioned, that's uniform, Bernoulli, von Neumann, Laplace, they're all combination of rejection sampling and geometric. And so if you look at the mass function for a specific outcome, they all combine these two patterns where they're going to be 0 for a while. And eventually, the values are going to be what, at least to me, looks like it's pretty chaotic. I don't know how necessarily how to describe it as a simple function. But eventually, in the same way that for geometric, at some point you get a value that's stable, here's not going to be a value. It's going to evolve, like with accept reject, but it's going to evolve following typically a very simple function. So to show, to characterize these PMFs, the method that we ended up using, which I'm not claiming it's simpler than other methods or anything like this. It's just that's how I was able to cope with the complexity. The proof is split in two. And so for each outcome, we're going to prove that eventually the mass will evolve according to some simple function P(O) of I. And the first part of the proof is you show that at some iteration, the mass is going to start being P of I. And for any unfolding greater than I, it will continue evolving as such. So it's kind of a variant of a Scott induction principle in some way, except that we only show the result after like some number of unfolding where the mass function has become simple. And we can conclude with a variant of monotone convergence. The other part of the proof is to show that once you've characterized the distribution, that it satisfies concentrated TP. And here, the key, the proof is not for me, is to use the Poisson summation formula. So here again, very useful to have MATLAB because we need to have this result. In the paper, it's a fairly short proof. It's like half a page. For me, it turned into quite a journey in Lean. I don't think there's that much interesting to say about it. But note that, first of all, the summon function is projected from being of type integers to extended non-negative reals to complex numbers, because we need to use results from Fourier analysis. And it's also very convenient for lots of reasons. In particular, we use a special case of the Jacobi theta modular form to show all kinds of convergence results for the summoned and the Fourier transform. And we do this because there are results in Lean about this. And to me, that sounds pretty fancy. But what's interesting about that proof isn't mostly what I just said, but it's actually that I don't know what the Jacobi theta-Miller form is. I needed to prove convergence results to get to the Poisson summation formula. And to do this, I use grep and other tools like a sim question and apply question. But basically, by grepping for results that would allow me to prove that result faster, I end up like stumbling upon this object, the Jacobi theta-Miller form, and it was fantastic because it saved me a lot of time. I estimate that it probably saved at least 2-3 weeks of work by being able to piggyback on that library. So whoever implemented, verified this Jacobi theta-Miller form, I thank you because it's been fantastically useful. But again, the thing is, and that's the magic for me of MATLAB and of Lean and of formal verification, and of the fact that we know everything we're doing is sound, is that yeah, I end up using objects that I don't understand. So it's not the only case, but that's one of them. Note, however, that at some point I ended up being stuck because eventually what you've proved from the reals to complex, you have to go back to my mundane function that's going to be deployed. And that's one case where I could not grep for it. And maybe you'll find this an interesting anecdote, but one day I was tired, I couldn't figure out how to do it. And I said something preposterous, trying some AI for fun, saying something like, oh, I need to do like the convergence result, I need to do a topological switcheroo. And it suggested this thing. And I don't know what a filter is, but it turns out that after a little bit of digging, that's the theorem I needed to conclude my proof. So to me, that's something else that I find interesting, and that's really the beauty of both MATLAB and having an AI that can help me figure out the details of my proof. I should wrap up quickly. So some numbers, it's 500 lines of code. The proof at that point in time was 11,000 lines. It took me 8 weeks to write the proof. Some methodology details. I try as much as possible to avoid dependent types or like index families or things like this. And I try to maintain a clean separation between the code, which I write essentially in a subset of ML. I keep things simple and have the spec and the proof on the side. And the performance is very good. That's what the figure on the right shows. The red curve is the extracted one, but keep in mind, of course, it's C++. But the yellow one is still Lean extracted to Python. So the performance are very decent. To conclude, the code is available. It's open source. There is a paper that I wrote with many of my co-authors, and I'd like to, in particular, single out the first author, Marcus de Medeiros, who was an intern with me and who is a grad student at NYU. He's contributed a lot to SAMCERT. And in the paper, you'll find many more interesting things about, we introduced the idea of abstract differential privacy. We talk about other important operations like composition, queries like unbounded mean histograms, etc. And that's it. That wraps up my talk. Thank you.